Next, I want to do a few examples. Okay, so we're going to do a few examples of applications of Cauchy's integral formula. So let's start here. Let's evaluate. So let's evaluate the integral of z plus 5 over z squared minus 1, where we integrate over the positively oriented circle centered at 1 of radius 1. Okay, so this is going to be some circle centered at the complex number 1 plus 0i, and it's going to have radius 1. So it's going to look something like that. Okay, just pretend it's a circle. Okay, something like that. Okay, so what we need to do is we need to think about whether the conditions of Cauchy's integral formula are met. And so we need to look at this function here. First of all, we need to recognize, we need to think about how this is going to work. This is going to be the integral of z plus 5 over z plus 1 all over z minus 1 dz. And so our f is actually going to be this z plus 5 over z plus 1. And again, we're integrating over the circle centered at 1 of radius 1. Okay, now here our f of z is z plus 5 over z plus 1. And that's going to be holomorphic everywhere except at -1. But -1 is over here. So in particular, on our region, or on our, in this circle, you know, you can take some open set that has this disk contained inside of it. Everything's fine. And Cauchy's integral formula applies. And also the circle centered at 1 of radius 1 is positively oriented, piecewise smooth. In fact, it is smooth, closed and simple. So everything's fine. And what's going to happen here is that because all the conditions are satisfied, this integral of z plus 5 over z plus 1 divided by z minus 1 over the circle centered at 1 of radius 1 dz is going to be equal to 2 pi I times f of 1, where f was this function. And f of 1 is going to be 6/2. So that's 2 pi I times 6/2. So this is 6 pi I. Okay, so there's one example. Another example I wanted to talk about was the integral of e to the z over z dz, where we're going to integrate over gamma, where gamma is going to be the positively oriented square with vertices 1 plus I, -1 plus I, -1 minus I, and 1 minus I. And again, positively oriented. So it's going to look like this. Okay. And from there, what we can do is we can apply, again, Cauchy's integral formula. So e to the z is going to be our f. So our f of z is e to the z. You notice that 0 is inside. So 0 is inside gamma. Okay. And from here, this is going to be, so this integral, e to the z over z over gamma is going to be 2 pi I f of 0. And it's just 2 pi I. And that's much nicer than, I mean, just try it. Come up with a parameterization. It's almost comically difficult. Come up with a parameterization gamma over here. In fact, it might be impossible to do this any other way because e to the z over z doesn't have an antiderivative. And so there's nothing that you can really do here. But by Cauchy's integral formula, we can still evaluate this integral and find out that this is going to be 2 pi I. Okay, so that's particularly nice here. All right. One more. Let's look at, so one more example. Let's look at the integral of sine of z over z, as we're going to integrate over some circle centered at 0, radius r. I don't care about the radius, dz. And again, sine of z over z does not have an elementary antiderivative, but everything is fine. Sine is holomorphic everywhere. So it's an entire function. This curve is closed, simple, piecewise smooth, positively oriented. So we're assuming that we're going around in a positive orientation. And again, this is an entire function, so it's holomorphic everywhere. Everything is fine. So what's going to happen is we're going to get 2 pi I times f of 0, where f of z is sine of z. And of course, sine of 0 is 0. So it turns out that this function is still going to be 0. Okay, this integral, excuse me, is still going to be 0. Okay, and so there's, yeah, some examples of Cauchy's integral formula. I don't really have too much more that I want to say here.